Hello, welcome back to Chemistry 2341. Sorry about last Wednesday. So a weird thing happened to me is that I woke up Tuesday morning like I always do about 5 a.m. About 5:30, I went into AFib and had to go to the hospital. So it's just a fibrillation of the left atrium of my heart. It's not immediately concerning, except that it can form blood clots, and therefore I had to go to the hospital to make sure it doesn't do that. It's not like a heart attack or anything. I didn't do anything like that, but I had to just wait around until it corrected with medication. I've had it a couple of times before, and they usually shock me, kill me for 10 seconds, and then it comes back normal. But they didn't do that this time. So hey, I got out easy this time. But so that's why I couldn't hear, and I'm sorry. But hopefully you saw some other lectures over there. But I'm going to pick up where I left off because I figured out how to make up time I'm going to pre-record my reviews for the exam, so you can watch them and study as you go. And then I'm going to lecture up to that day. And then you'll just have that review on your own. So that's how I'm going to make up for that time. So let me go ahead and share my screen. And I think it's sharing now. There it is. All right. So when we left off, we were talking about Sn2, substitution, nucleophilic, bimolecular. Both molecules have to be there at the exact same time to make it happen, right? And we said that there are several effects that affect the nucleophilicity and or rate of the reaction, including things like temperature, but the most critical one here is solvent, okay? And there's two types of solvent we're dealing with. We're dealing with a polar protic solvent, which is one that, like an alcohol, water, or a carboxylic acid that has a hydrogen bonding hydrogen. And then we have a polar aprotic solvent, which does not hydrogen bond, okay? So the key here is that in polar aprotic solvents, that halogen, which is our nucleophile in this case, is not very well solvated. And so it is not as easy to go. And so it's dominated by the acidity of the, it's not dominated by this, it's dominated by the type of charge we have, which is why in a polar aprotic solvent, fluorine is the best nucleophile and iodine is the worst nucleophile. But when it's hydrogen bonded to it, right here, in the protic solvents, it's actually the solvated nucleophiles are less reactive, and therefore you have to have a better nucleophile. So in that case, your iodine is more reactive and your fluorine is least reactive. This happens mostly in the halogen series, but you want to think about either a polar or most of the time we do it in a polar aprotic solvent, unless we have the halogen, and then we decide which one to use, depending on whether we want fluorine to do the substitution, and we use a polar non-protic aprotic solvent, or we want iodine to do the work. So if we want to put iodine on it, we're going to do it in a protic solvent. We want to put fluorine on it, we want to do it in an aprotic solvent. So I wanted to draw attention to that, and that's one of the weirder things about that system, okay? So in review of all Sn2 reactions here, it's bimolecular. You have to have the concentration of both ingredients, the nucleophile and the substrate, are important, okay? The transition state involves a single transition state of making and breaking a bond at the exact same time. It really helps with the leaving group. You want to move to the weaker base. So you look at the base strength of your nucleophile and the base strength of your leaving group. You want that base strength of the nucleophile to be weaker than the nucleophile to make your reaction go, okay? So in reactivity, we have strong unhindered bases are good nucleophiles. Now, what I mean by that is like methanol and ethanol, the salts of those, because they have very little steric demand and they can act as a nucleophile, okay? If you have a big bulky one, remember, it can't get close enough to the substrate to start forming that bond, and therefore it acts as a base. We're going to see that in chapter 7 when we talk about elimination reactions. So they make it very poor nucleophiles, and we don't typically use them as nucleophiles. We'll use them as a base in chapter 7. Now, weakly polarizable bases are good nucleophiles. I'm sorry, weak and polarizing bases are good nucleophiles, like iodine and bromine, especially when used in a Protic solvent. And the less polarizable bases are poor nucleophiles, things that don't have a charge, things that are relying on that lone pair to do the work, okay? So polar aprotic solvents speed up the reaction, okay? And it also makes fluorine the better nucleophile. Polar protic solvents slow down the reaction and encourage iodine and bromine to act as nucleophiles. Okay, questions on that? Okay, all right. So now there is a strong component on this where you can trick it, okay? And we can trick it by taking a look at what we think is the thermodynamic product, but we can have something do it such that it does a phase change so you can trick it into its kinetic product instead, okay? So let's take an example of this reaction here. We have iodine as our leaving group here and chloride as our nucleophile coming in here, okay? So we have to think that it's going to go to the chloride anion because that chloride carbon bond is shorter, and therefore that chloride carbon bond is stronger. Therefore, it is the it's the better nucleophile, and this is the more thermodynamic product here, okay? But let's think about that. Which is the stronger base, okay? Iodine is the strongest acid. So HI is the strongest acid. HCl is less strong than that, which makes the conjugate base of each of those. Chloride is the stronger base than iodine. So it's thermodynamically driven to give us a chloride there instead of the iodine. Okay. But there's a way to trick it. Okay. And we can trick it and make it go to the kinetic product. Okay. So how can we trick it and go to the kinetic product? Well, we trick it and go to the kinetic product by, even though there's a little bit of forward inverse, there, remember this reaction is slightly reversible, but what if once we got that stronger base, the chloride, and turned it into a solid and removed it from the solution? So it's no longer participating in the reaction because it has turned into a solid. Notice we're still using acetone here, but notice sodium chloride is not soluble in acetone, and the sodium iodide is. So we know the reaction's reversible because as we make it, a little bit of sodium chloride is going to start precipitating on the reaction. And we can actually force it to that kinetic product, that product with a weaker bond. Okay, and we are taking the stronger base and dropping it down. Now, in this case, we have a polar aprotic solvent. Okay, a polar aprotic solvent means fluorine is the most reactive. So that means chlorine should be more reactive than iodine, okay? So we have the, it should have ended up as the chloride product because that's our thermodynamic product. But because we're taking it out of solution, we're tricking it to the kinetic product. Even though it's the least, it's a less stable bond, it will form that product by that participation. Question on that? So all of these are reversible, and to some extent, although most of them tend to lie toward the stronger bond or toward the weaker base. Okay. So let's talk about the effect that the substrate has on the reaction. And so part of it is sterics, right? Because we have big things are inhibiting the attack angle of our nucleophile to come in and start forming a bond when we're breaking our bond. Which means that things that have very little demand on them, like 3 hydrogens here, makes it easy to come in and start forming that bond in between those 3 hydrogens and have that bromine leave at 180 degrees, okay? So let's start with something like this ethyl bromide, and we have that alpha carbon, that's the carbon that the halogen or the leaving group is attached on. And when it's a primary carbon, we're going to call that a relative rate of 1, okay? If we take that other carbon off and put on a hydrogen here, it goes 145 times faster, okay? Just the little methyl group here is inhibiting the reaction that much, okay? So if just that one methyl group is inhibiting that much, well, what if we put another one on there? So now we have a secondary carbon right here, and it is going at less than 1% the rate of the primary, okay, just by adding that methyl group. See how big that, and the methyl groups aren't very big. So the fact that they have this big a steric hindrance on them and slows the reaction down so much, very interesting. And then by the time you put 3 here, technically they don't do Sn2 reactions. You might get a little bit of product eventually, but it's not going to go at any appreciable rate. So the type of substrate you have controls your kinetics in an Sn2 reaction. And it makes sense because you have to be forming the bond and breaking the bond at the same time and 180 degrees apart from each other. Okay. So, and we can look at that from the perspective of the idea that the nucleophile is not just the nucleophile, right? The nucleophile has solvent around it to support it, right? So when your nucleophile is starting to come in and it only sees 3 hydrogens here, it can easily push them out of the way because they're small atoms. This is a larger atom, and it'll have enough kinetic energy to do this. Come in and start forming our bond here at our transition state, and then have our, but when we put these methyl groups here, those are much, much bigger. And our nucleophile still is taking up the same amount of space. And so trying to come in and form this transition state is very difficult. And that means it has a much higher activation energy. And so you either have to heat it really high for a really long period of time, or just try to do it by a different way. Trying to do a tertiary Sn2 reaction is very, very difficult. Okay, so let's look at the effect of moving over a little bit. Obviously, this is the same kind of relative reaction rate we just saw in the previous one, but what if the big group isn't attached directly to the carbon that we have our leading group on? That still has an effect because remember, it's solvated and you have the free rotation of the sigma bonds, and there's still some effect. And what we see here is if we have a primary carbon with our methyl group, we have a relative reactivity of 1. Notice that's the same as this one up here, okay? By moving, by adding 1 carbon toward the end of the chain, it slows it down about 20%. Okay, so we still have the same kind of group here, but the fact that this has a rotation on that sigma bond, it can flip around in space and gives a little bit of steric demand right here. By having another methyl group on that 1 carbon over, it drops down to now 3%. Okay, so this group right here is free rotating around this sigma bond. Imagine it's almost like a barbell flipping around in space. That's giving enough steric demand that it drops it to 3%. And by the time you put 3 of them on here, even though they're 1 carbon over, you still have a primary alkyl halide. Imagine you have a propeller now flipping around there, and it's just blocking all the nucleophiles from coming there, and it drops down to less than 1/10 of 1%. So even though these are all primary carbons, and in theory, they should have a high reactivity rate, the fact that we're substituting on that beta carbon, 1 carbon over from the carbon that leaving group's on, these are still flipping around in space and still count toward the steric demand of your reaction. Questions on that? Okay, so now we have another group to actually helps activate our system too. Now, if you have an sp2 carbon with a halogen on it, they don't undergo substitution reactions, okay? They don't undergo substitution reactions. However, if you have an sp3 hybridized carbon next to an sp2 hybridized carbon, it actually activates the system, okay? And I'll show you why on the next slide here. So if we look at our relative rate of just our methyl group here as 1, our primary, just putting a methyl group there, drops it to about 33% of that. And then our secondary, of course, drops down again. Okay, now, if we have an allylic system, and that would be this here, meaning we have our beta carbon here, this is sp2 hybridized, okay? it's going to make it go faster than the methyl group. But sterics, well, no, remember, all reactions are a competition between sterics and electronics, okay? And we can do the same thing with having a benzene ring here. This also has a double bond. These are kind of, these double bonds are flipping around this ring very fast, and it even speeds it up even more. It's 4 times faster than that methyl halogen, that methyl halogen right here. Okay, but it's sterically demanded. It has there. But again, it's the electronics of the issue. During the transition state, right here, as our nucleophile is starting to come in and form our new bond with our carbon, and our leaving group is starting to break that bond. Remember, we're transitioning through a square planar with a p orbital is forming on either side as we go. And that p orbital is aligned with the double bond on that adjacent carbon, okay? Because it can donate electron density and help align this, this transition state, it actually speeds up the reaction. The sterics are out of the way because they're actually lined up with the p orbital and this new intermediate transition state. And then of course, when the leaving group leaves, we relax back to our sp3 hybridized state. Okay. Same thing happens with benzene, but we have just a ring out here. And we have that same thing where we have the lone pair from the benzene ring is help stabilizing this portion of our transition state. And that activates the bond toward our thing. So basically having it aligned with the p orbitals here lowers the activation energy and speeds the reaction up. All right, so, but again, we don't actually do Sn2 reactions on the actual sp2 hybridized carbons here. They don't undergo that reaction because number one, this is in an sp2 hybridized, it's not tetrahedral, it cannot form that transition state. It doesn't undergo an Sn2 reaction. Okay, so you can have these halogens all over the place on your system, but it's only going to react with the sp3 hybridized halogens as leaving groups. Okay, and the last thing I want to talk about is intermolecular versus intramolecular. So intermolecular is you have one compound here, and they have to diffuse around and find each other and have the right energy and have the right angle to react, right? So, well, okay, what if we took one end of the molecule and turned it into a nucleophile and the other end of the molecule had a leaving group? So now they don't have to diffuse around, they just have to use their free rotation, and they can just use their free rotation until they come into that correct angle. And as it turns out, these intramolecular interactions are 5,000 times faster than the intermolecular reactions. They don't have to diffuse toward each other because you have 100% of reactive group within a few angstroms of 100% of your carbon with your leaving group. And therefore, the probability of it having enough energy and the angle and the number of times they hit is much, much higher because of the close proximity. And that means the reaction speeds up. So we can form these nice cyclic materials like this cyclic ester called lactone, or a cyclic ether called tetrahydrofuran. All right, so that's the end of chapter 6.2. And if there aren't any questions, I can go to 6.3. Yeah, my mic's on. All right, good, just making sure. Okay, so let me pull up 6.3. Okay, so the first thing we learned is a lot about mechanisms, about the reaction diagram and the fact that we have a bimolecular reaction here, and the concentration of both things is very important. Well, there's another type of reaction we can do, and it has to go through a different mechanism. We call it an Sn1 reaction, unimolecular, meaning that you have to break a bond first to make an intermediate that's actually going to be attacked by the nucleophile. Now, because you're breaking this bond first and forming a carbocation, it only depends on the concentration of your substrate, the thing with the leaving group on it, okay? So in this case, we only care about the concentration of our organic compound with our leaving group on it. And therefore we call it a first order reaction because the little power up here is 1. And the 1 stands for unimolecular because it breaks a bond to form this intermediate first. So how does that affect the reaction diagram? Okay, well, that means the reaction diagram has to be a little different. Okay, in the reaction diagram, the first step is going to be breaking a bond. Okay, that's one of those 5 things that we said we could do in a mechanism: add a proton, take a proton away, break a bond. In this case, we're breaking the bond heterolytically, where we're having one thing leave as an anion with both electrons of that sigma bond, and the other one's leaving as a cation. Let me blow that up. Okay, so when we do that, it takes this huge activation energy just to break that bond. But what does that leave us? That leaves us something with a cation on it. And in this case, it's going to be the carbon. And something with an anion on it. In this case, it's the chlorine. Okay, notice that this intermediate right here is still very reactive. Okay, and it's in higher energy than the starting material. Okay, so it's really reactive because it just stored a bunch of energy and it's trying to react to get rid of it. Now, the cool thing is we have this p orbital now. Notice we've changed our hybridization here. We're now sp2 hybridized and we have an empty p orbital. Okay, so the methyl groups here are all trigonal planar, and you have a lobe of the empty p orbital above and a lobe of the empty p orbital below. Okay, which means that now we can have even weak nucleophiles. In this case, water can come in and react with that positive charge to give us our next intermediate. In this case here, it's a protonated form of the alcohol. And then when we lose that proton through a third transition state, we get to the final products, our neutral molecule plus HCl and water. So the key for our system here is we always have a second activation energy because we always form an intermediate here. And the intermediate is always a carbocation. Okay, so let's look at that a different way. Okay, so in the case of our Sn1 reaction, it's unimolecular, which means we have to break a bond first. So the first thing we do is break our bond, form our carbocation. We've changed the hybridization here. We have an empty p orbital, okay? And that means even weak nucleophiles can come around and react. Okay, now, what it also means is that you can have your nucleophile come in from the top or the bottom because it's the p orbital. It's equal on both sides. So we're going to have to pay attention to that because that's going to change what we saw in our Sn2 reaction, where it always gave us inversion of stereocenter. It's going to change for this reaction. Okay. So again, the first step is we have our highest activation energy is breaking that bond to give us our intermediate. So our transition state is technically just the taking of the electrons from this sigma bond and putting them on the chlorine and leaving our rehybridized intermediate here. So now it's very reactive because it has a lot more energy than the starting materials had. Okay. So then the next thing that happens is our nucleophile. Notice it's just the lone pair. It's not even a charged nucleophile required. The lone pair is going to share with that positive charge right away. And in this case, we're going to use water as our intermediate here. And notice that as the electrons come in to form this, to start interacting with that p orbital, that empty p orbital, we've changed hybridizations again. We've changed back to our sp3 hybridized, our tetrahedral structure, okay? But we have a charged species. And so we have to use something in the solution to act as a base to remove that proton to give us our neutral species in the end. Okay, that's if we attack with a neutral poor nucleophile. If we attack with a charged nucleophile, something with a negative charge, we wouldn't have that third step because we would have created a neutral product in the end. Okay, so I said that in an Sn2 reaction, because we're forming and breaking at the same time, we're inverting that umbrella and we're getting inversion of stereocenter. Okay, what happens when we go through the carbocation? That carbocation is trigonal planar with a lobe above and a lobe below, and they're equal. So the nucleophile can attack on top or attack on the bottom. So if we looked at this one right here and we had this S configuration here, and we just boiled it in water, it doesn't even take much, just boil it in water and with some acetone to help solubilize it, what we're going to see is we're going to get some of it is going to be S and some of it's going to be R. But how much of which one are you going to get? Is there a difference between the two halves of the p orbital? No. So you're going to get 50% R and 50% S. So you're going to get a racemic mixture that's optically inactive from the system. Remember that racemic mixture is a 50-50 of the R and the S. So whenever we have an Sn1 reaction, we have to worry that we're going to racemize, which means make a racemic mixture out of the system. Okay, so, and this will work with anything. In fact, what you can do is help probe your reaction by doing your reaction on a chiral substrate and looking to see if your product is optically active or is not optically active. If you start with an optically active material and it comes out optically active at the end, that means you went through an Sn2 type reaction because you had an inversion of your stereocenter. If you lose all optical activity, then that means you have a mixture of R and S, and therefore you know you went through an Sn1 mechanism. Okay, so there's a bunch of different types of reactions we can see in Sn1. One of the really common ones is where we use the solvent as the nucleophile, and we use something like water or ethanol. And we're going to form either an alcohol or an ether from them. And these are really, really weak polar protic solvents. I mean, nucleophiles, because they don't have a charge, okay? And when we do these reactions where we're using a solvent as the nucleophile, we call this solvolysis. So we're actually using it as the solvent and the nucleophile at the same time, and it drives the reaction to completion from this. Now notice all of these are polar protic solvents. Carbocations in particular are really, really useful, or really formed much more easily in polar protic solvents. Okay, so if we used water, we're going to end up with an alcohol after our protonated alcohol is reacted with to form HBr. If we used an alcohol, we're going to end up with an ether here. Okay, and that would be protonated when it first forms, and we'll have to lose that proton to make the neutral molecule. And we can even use, in this case, formic acid or a carboxylic acid. And what it's going to form is it's going to form an ester. Okay. And so with water, it's hydrolysis. With ethanol, it'd be ethylysis. And with an acid, it'd be acidolysis. Okay. So I said polar protic solvents are really commonly used in Sn1 reactions. And it's partially due to the fact that because it's polar and protic, the leaving group is hydrogen bonded to very well by the solvent, okay? Which makes the leaving group easier to leave with, okay? Now, and in addition, the other half of the molecule, the partially negative side, can help stabilize the carbocation. But notice over here that your leaving group is hydrogen bonding to multiple ions here, multiple hydrogens from the solvent there. And that's what makes it easy for it to leave, because notice that it can actually reversibly go back and forth here. It's just being held in that position. And then when that happens, you can have reaction by, in this case, the solvent to give us our new product. Okay. Okay, so why does that happen? Well, the fact that you're partially hydrogen bonding to your leaving group before it even leaves it lowers the activation energy, okay? Because it's partially hydrogen bonded before it leaves, it lowers the activation energy. Therefore, it makes it easier to go. So for example, if we did our reaction in something like methanol, we can actually partially start tugging on your leaving group before, and that gives us a lower group. Now, if we did that same reaction in acetone, which is not polar or less polar, it's going to form a lot slower and take a lot more energy to hit that transition state. So we're going to see it being faster in your polar Protic solvents and forming that carbocation. Okay. So just as an example here, if we used water, 100% water, and just boiled it, our T-butyl bromide here in there, we would have, the product would be T-butyl alcohol and HBr. And our relative rate is going to be 400,000 times faster than if we used acetone, which can only dipole-dipole interact, and only enough water to actually make the reaction go, okay? So because we have so much more acetone, very little hydrogen bonding is going on with the bromine here, and that slows the reaction down significantly, okay, because of that higher activation energy. Questions on that? All right. Okay, so our SN1 mechanism occurs in polar Protic solvents. In fact, you almost have to use them, okay? So this is something to pay attention to when I say, is this an SN1 or an SN2 reaction? Let's start looking for the solvents and the products here. It's different from the SN2 reaction where polar aprotic solvents increase the reactivity, okay? Remember, in an SN2, we're trying to make the nucleophile a stronger nucleophile with the aprotic solvent. And in the case of SN1, we're trying to hydrogen bond to the leaving group to pull it off first to form our intermediate. So that's one way to look at the difference between the SN1 and the SN2. Okay, our SN2 reactions will occur faster. Let's see, in polar Protic solvents, but they're faster in polar aprotic solvents. And SN1 reactions don't really like to work in polar aprotic because you have to put so much more energy to get to the transition state. Okay, there we go. All right, so let's look at different solvents and what we think their relative rates are here. Okay, so if we look at water, methanol, and ethanol, those are all really good solvents, really cheap, nice to use. They're all Protic right here. And this is E, this is the dielectric constant. This is basically telling you kind of it's a relative to the dipole of the system and how strongly it solvates things, okay? And we tried to do the ionization, basically, of tert-butyl chloride, which means we're gonna do that first step. We're making that intermediate, that carbocation of the T-butyl chloride. So we're trying to make that carbocation, and we're looking at that relative reactivity. So if we did an acetone, it would have, and we call that 1, and say, okay, it took an hour to make, 20% of the substrate convert to there. Well, it'd be 200 times faster in ethanol, okay? But it would be 1,000 times faster in methanol because it's more polar than the ethanol, and it'd be 8,000 times faster in water, which is the most polar of the set. So you can think about this as a relative trend in polarity. The higher the number, the more polar the molecule. Okay. Now, as we go to non-polar systems, like diethyl ether is not very polar and it's aprotic, it is going to be less than 0.1% as fast. So it's going to be 1,000 times slower, okay? And when we go to something like hexane, which can't support the ion that it's trying to break into, can't support those ions at all, it goes down to almost negligible. You almost can't measure it. Okay. So this is the power of the polar Protic solvent in the SN1 reaction system. Okay. Okay, so now let's compare and contrast. SN2 is a bimolecular reaction, has one hump in the transition state. Okay, the simplest SN1 transition state has 2 humps. Okay, that means that you have to form your carbocation intermediate here, and then something else has to happen to react with that. In the case, if you form a neutral molecule, you only have 2 humps. If you're attacking with a neutral molecule and form a charged intermediate, then you have to lose that proton and it'll have that 3rd hump. Okay, so they tend to, the polar protic solvents tend to make them go faster than the polar aprotic solvents, but they still happen in Sn2. Okay, and in the case of Sn1, the less polar solvents, if they are not protonated, then the reaction almost never goes. But if they are protonated or a strong dipole, they can go. And of course, the polar protic solvents are much easier to make, much faster reaction reaction because that lower activation energy. And this one, the nucleophile is donating its electrons. Remember, it's a Lewis base, and so we're donating our electrons to start forming the bond while we're losing electrons with the leaving group. In the case of the Sn1 reaction, we actually formed an ionic intermediate, and therefore the electrons that are coming in from the nucleophile can either be a lone pair or a charge. But it must be forming that carbocation intermediate. And let's see, I already said the polar stuff. This intermediate that forms, the carbocation that forms, must be stabilized for the solvent or it won't work. Okay. So that's the difference between Sn1 and Sn2. But we also have something about them. Notice that all the examples I had were using tertiary halides. We had the halogens were all on T-butyl groups. In the Sn1s, we saw that those primary and those methyls worked really, really fast. And by the time we got to a secondary or tertiary, they went much, much slower. Okay, so just the nature of the substrate is going to give us an idea on which mechanism might be happening. Okay, so let's look at that relative reaction rate for Sn1. Okay, we did that for Sn2, so let's do it for Sn1. Okay, so in the case of this, it's the opposite order for Sn1 than it was for Sn2. Tertiaries are fastest, okay? There's gotta be a reason for that. Secondaries are next, then primaries, then methyls. In fact, primaries and methyls almost never do an Sn1 reaction. It's very difficult to do that. Why? We have to think about its intermediate. We have to stabilize that intermediate, and the most stable carbocations are tertiary carbocations. The methyl right here, the methyl carbocations and the primary carbocations are very unstable in solvents. You can probably only make them in gas phase. The secondary and tertiaries are pretty stable in solvents. In fact, especially if it's a polar protic solvent, they can help stabilize that charge. In addition, just like we saw with the reactivity of the group adjacent to a vinyl group or a double bond or a benzene ring here, these actually are quite stable as well. And they're not stable because they have 3 substituents. They're stable because they have resonance structures. They're resonance stabilized. We can have the cation, even though it looks like a primary cation, it's actually resonance stabilized over 2 carbons. We can have that positive charge on 1 carbon and on the 3 carbon, and it'll go back and forth, back and forth. So those allylic positions, this primary alkyl halide actually can undergo an Sn2 because of the conjugation. Same thing happens in benzene rings. We can just flip the positive charge all the way around the ring or have it here. So even though they look like primary halides, they're actually resonance stabilized cations. Okay. So just to remind you, we talked about carbocations. The more substituted the carbocation is, the greater number of carbons they have. You have an inductive effect, helping stabilize it. Then you have that hyperconjugation effect from the hydrogens that are adjacent to the, excuse me, adjacent to the p orbital, that empty p orbital. And so you can have the stabilization from there. Okay, so you have hyperconjugation effects and your inductive effects. Now remember, our carbocation is an empty p orbital, right? And so if we have an empty p orbital next to a double bond right here, that is going to line up and allow it to resonance stabilize going back and forth between the two sides here. And so neither one of those methyls, neither one of those primary carbons actually carries a full positive charge. It only carries half a positive charge. That's why it's more stable than the methyl cation would be. There's no hyperconjugation effects and there's no inductive effects. The hydrogen just can't donate anything back. Okay. All right. So let's talk about the difference in activation energy from the different systems. Okay. So in the case of primary, secondary, and tertiary, it has everything to do with that hyperconjugation and then inductive effect, changing the activation energy. Because this is stabilized by those hyperconjugation and the inductive effects, it has a lower activity to get to that intermediate. Because this isn't as stabilized, we have a higher activation energy, and therefore it's a slower reaction. And by the time you get to a methyl, these are so high that you probably can't add enough energy to the system to get them to go very much at all. So we call them, they really don't go very often. So the primary might go a little bit, but methyls don't undergo. I would just say methyls and primaries don't undergo Sn1 reactions. Okay, so, but if the hyperconjugation and this induction makes the tertiary the most reactive of that set, but having that resonance contribution makes them even more reactive. So the allylics are faster than the tertiaries and the benzylics are much faster or equal to the allylics. The idea that we can stabilize that positive charge over 2, or in the case of the benzylic position, 4 carbons means that it can be a relatively stable system and relatively easy to form. Okay. So, but again, we cannot do an Sn2 reaction on an sp2 hybridized carbon. It doesn't work. We cannot form our carbocation in this position here. It's just not available to us because of where the carbocation would have to be sticking out in the system. It just wouldn't work. So we do not see vinyl or aerial halides react under Sn1 conditions at all. Okay. So the next thing that affects the rate is the idea of what does the transition state look like, okay? So when we think about the Hammond principle, we want to say that things that are more like the starting materials are, okay, the things that are more like the starting materials are going to be more like, let's see, are going to be inorganic. We're gonna, by the things that look more like the starting material are going to be more exergonic than endergonic. But here we have our intermediate that's actually going to look much more closer to our product. So it's going to be that higher internal energy. Okay. So when we did the Sn1, we looked at, when we did the Sn2, we looked at the effect of having groups adjacent to it. But with the Sn1, we're always forming a carbocation, right? And one of those things that we can have in a mechanism besides adding a bond or breaking a bond or losing or adding a proton is what we call rearrangement, okay? And in the case of carbocations, tertiary carbocations are more stable than secondary carbocations. That gives rise to what we can call a migration or a shift right here. It's going to be a 1-2 shift, okay? And so this is a carbocation rearrangement. And the driving force is that it wants to be the most stable carbocation it can be. And so it can either move a methyl group 1 carbon over, or a hydrogen 1 carbon over to make it more stable. It's only going to move 1 carbon. It's only going to move 1 time. Okay. So in the case of having a secondary carbocation here, okay, it's going to say, hey, I'm a secondary carbocation, but hey, I can be a tertiary carbocation if I just take these 2 electrons right here, move them over to one position, and then rehybridize this to give us our carbocation. So we've done what we call a 1,2 methyl shift, because we're moving from 1 carbon to the 2nd carbon over and getting that more stable carbocation. We don't have to move a methyl group. We can actually move a hydrogen. But we call it a hydride shift because it's taking both electrons with it when it goes. So it's going to move over 1 carbon to give us our electron shift and give us our more stable carbocation. So this becomes a problem if you're doing an Sn2 reaction on a secondary halide, because you will see rearrangement in the system. Okay. And the whole reason it can move is the idea that you have an sp3 hybridized bond here, sigma bond, and it can sort of line up with the empty p orbital here first. Once it sort of lines up with there, it can just transfer its electrons over 1. So notice it's sharing electrons. It's starting to move its electrons from here to here and gives you your more stable empty p orbital. Notice that there's hyperconjugation between 3 different sigma bonds here to give us that stabilized tertiary carbocation. There was only 2 in the case of the secondary carbocation. Excuse me. Oh, it's gardening this weekend, and apparently I got too much mold. Okay. So what we're going to see here is that there's going to be 2 types of carbocation shifts we see. Okay. So there's going to be the 1,2 shift where we only move once and we only move a methyl group or a hydrogen. Okay. The other kind we can actually see is we can actually open a ring up, and that will seem it's still moving 1 little methylene unit and it's only moving at 1 carbon, but we're going to see rings open up as well. Okay. So let's look at the reaction diagram for a carbocation rearrangement. Okay. And we're going to see what the driving force is. Okay. So if we look at our first transition state here, it's pretty high because we have a secondary alkyl halide here, giving us our transition state of breaking that secondary halide bond, giving us our secondary carbocation. Okay. Our secondary carbocation is much higher in energy than our starting material. And therefore, but the driving force is the idea that our tertiary carbocation actually can be less in energy, or at least much closer to our starting material. And that's the driving force for it to go from that secondary carbocation to that tertiary carbocation. Once it gets to this more stable intermediate, it can wait around to react with whatever nucleophiles around and give us our final products. Note the thing is exothermic netwise, and it's exothermic from our first intermediate, which is our secondary carbocation, to our second intermediate, which is our tertiary carbocation. And that's an exothermic reaction as well. And then, of course, our neutral material at the end is also exothermic. Questions on the carbocation rearrangement? So when I give you a question in the homework of, here's my secondary alkyl halide, what's the major product? You should be looking for the major product to be the one where it has rearranged to form its tertiary carbocation. Okay, so what's that look like? Well, okay, first of all, we are doing an SN1 reaction, which means we're going to get inversion of stereochemistry. So we got to play with that first. Okay, but what will also happen is we might see a shift in where the reaction goes. So in this case here, we're going to start with our compound here. This is our secondary alcohol, and we're going to go ahead and protonate that OH to make it a really good leaving group. And when we protonate that OH, we can form a secondary carbocation. Okay. And when we form that secondary carbocation, we can have the product be that secondary bromide here. But there's actually kind of an impurity in here, although it doesn't happen very much, is that you can get it to protonate again, give us your secondary carbocation, but then it'll do a 1,2 hydride shift to give us an internalized secondary that gives us in a little bit of yield here. So there's always a little bit of competition. You typically only see major products change when you're going from a secondary carbocation to a tertiary carbocation. Okay. But here's our second example. Here's our rings, okay? Now, just like before, we're looking at forming our carbocation. In this case, we're protonating an alcohol, we're forming a carbocation right here, and that's a secondary carbocation. Okay. Now, we have two things going for us in where we can move. We can move this methyl group over, but we can move this methyl group over. Okay. Which one's going to move? Well, let's look at that ring. That ring is 4 atoms, right? Those 4 atoms, that's a cyclobutane. That must have ring strain, right? Because it wants to be cyclohexane. That's the ring with no ring strain at all, right? And so we have 3. So we can either keep that ring closed and move the methyl group, number 7, up, or we can actually open that ring, relieve some of that stress, and give us a 5-membered ring and a tertiary carbocation. So what we're going to see is whenever you can go from a 4 or 5-membered ring to a slightly larger ring, you're going to see the ring expand. And it's called, and that's also found in those carbocation intermediates. Okay, questions on that? Okay, so, all right. So how can you tell which one's going to occur? Okay, SN1 or SN2. And that goes to what does the transition state look like? In the case of an SN2 reaction, the transition state looks more like the starting materials. Okay, and it's going to give off a fairly exothermic reaction to get to our product. We have that single hump to get to an exothermic process. Okay, in the case of our SN1, we're forming an intermediate. Our intermediate is the product of that first reaction here and is higher in energy than our starting material. Therefore, our product looks more like our transition state. Our transition state looks more like our product, meaning we're breaking the bond first before we ever form a new bond. And therefore, that's going to give us that endergonic or endothermic side of reaction. So we can look at the system as the SN1 is more starting material-like, and the SN2 is more product type. Okay. So how do you know what's going to happen? Well, the first thing you want to look at is the transition state. What is that intermediate going to be forming right here? So in the case of this right here, we have this methyl bromide here, and the concept that it can't form a stable carbocation as an intermediate is telling us that it's probably going to go with an SN2 reaction. It has two things going to it. A carbocation is very unstable, so we have energy going against it, and it has very little steric demand. So sterics are good, and energy of not going through that carbocation, going through that individual transition state is actually better. So our primaries and our methyls are going to be favored to do SN2 reactions because sterics and electronics are favored. In the case of tertiary, our tertiary has sterics not letting it do an SN2 reaction because of the sterics, and it can form a stable carbocation. So forming that stable carbocation is suggesting that it's going to go through that SN1 reaction, but not an SN2 reaction. So we're looking at the sterics are favored with the methyl group and the primaries, and the carbocations are disfavored because they're not as stable as an intermediate. In the tertiaries, we have sterics hurting us in our SN2 reaction, so it's not going to go. So we have a stable intermediate, so electronics are favored here. So sterics aren't favored, but electronics are favored, so we go through an SN1 reaction. Okay, so We're starting to look at substrates, sterics, and electronics kind of blending together to tell us which way to go. Okay. So let's take a number of substrates and think about that transition state, right? In the case of our methyl group here, we're going to start forming our bond. Oops. We're going to start forming our bond while we're breaking our bond here, okay? And that's going to give us that single transition state. We're not forming the carbocation, and our reaction coordinate is going to be just a single hump in our system. And this activation energy has everything to do with how good a nucleophile we have, how polarizable a nucleophile we have, and the ability of this leaving group to leave. Okay? So if it's a good leaving group and a good nucleophile, this is a lower activation energy. Okay. So when we have good nucleophiles on that list of good nucleophiles, we do that. But tertiary, to do this intermediate with the Sn2 reaction, we have such a high energy barrier here to get to this because of sterics that it just doesn't go. Okay. So we cannot get to this high energy barrier even with heat, even with a good nucleophile, because of the sterics of the situation. And therefore, it will not undergo that Sn2 reaction. It would prefer to go to the Sn1 reaction. Okay. So that means anything you have a primary and a methyl, it's probably Sn2. Any tertiaries, probably Sn1. But what about the secondaries? Okay, you can form a stable carbocation in a secondary. Okay, so that's the one we have to start paying attention to. Okay, so the first thing we can do is that our tertiaries will only go under Sn1, our primaries and methyl only at Sn2, but our secondaries can do either. In fact, they might be competing in the reactions here. But what do we look for to tell us the difference? Okay, three things. The solvent, okay? You want to think about your solvent. If it's a polar protic solvent, that stabilizes the carbocation. If it's a polar aprotic solvent, that does not stabilize the carbocation. What does that mean? Polar protic solvent might be able to go Sn1. Polar aprotic solvent might want to go Sn2 because it can't stabilize that carbocation. Leaving group. If you have a very good leaving group, something big, fluffy, weak base, iodine, bromine, okay, it might leave and break that early in an Sn1 type style. Let's say you have a worse leaving group, you know, something like a protonated water, or no, that's also good. A chlorine or a fluorine, that's a bad leaving group. It doesn't want to break that bond. That's a very strong bond. So those probably won't undergo Sn1, they'll go Sn2. The last thing we need to look at is the nucleophile. The stronger the nucleophile and the smaller the nucleophile, the more likely it is to undergo Sn2 reactions. The bigger the nucleophile and the weaker, like doesn't have a charge, it only has lone pairs, the more likely it is to undergo an Sn1 type reaction, where it forms the cation. The cation is now a much more reactive species, and that neutral molecule, that neutral nucleophile can come in and react. Okay, questions on that? All right. Okay. So let's look at it a different way. Let's look at it as relative reactivity rates versus sterics, okay? So if we look at our secondaries and tertiaries, right here, they can both undergo Sn1 reactions, okay? Because the secondary carbocation and a tertiary carbocation are pretty stable, okay? And because of sterics, the tertiary can't undergo Sn2, okay? So tertiaries, Sn1 only, no Sn2, okay? Because of primaries and methyls can't form stable carbocations, they don't do Sn1, they only do Sn2. And the smaller they are, the faster they go because of little steric interaction, okay? That brings us to the secondary, okay? Notice the secondary can undergo an Sn2 reaction, because it's starting to have some sterics, but it can undergo an Sn1 reaction because it has some electronics in its favor. Okay. So whenever you see this happen, you'll always see a solvent listed. Okay, your polar protic solvents encourage your Sn1. Your polar aprotic solvents encourage an Sn2. Okay, so every time you attack one of these problems, you can use these steps to help you kind of elucidate the thing. You want to make sure you add all your lone pairs because sometimes those lone pairs are going to be the things that are reacting. If you have a charge or partial charge on something, identify that. Okay, now figure out what is the nucleophile and what is the electrophile. Typically, the substrate, the alkyl halide, is the electrophile, and the thing that is charged or has lots of lone pairs is our nucleophile. Now you look at that electrophile and you say, okay, is it sterically demanding, or are there electronic properties that make it favorable for one thing or the other? So your allylic, benzylic, and tertiaries can form stable carbocations. So that's going to tell you Sn1. Our methyl and primary can't form stable cations, so we have to say that. And then our secondary, we now have to start looking at our product, at our solvent. So with our solvent, if it's polar protic, it can go Sn1. If it's aprotic, it goes Sn2. You should have enough information to figure it out just from walking through those steps in order to tell us Sn1 and Sn2. Okay, and if you can't, then you go ahead and start drawing arrows until it makes sense. Okay. All right, so here's a net summary slide. If you have to kind of study it like a flashcard to try to get where you are, you kind of want to look at this plus what solvents are polar and what solvents are, which solvents are protic and which solvents are. So the first thing we want to look at is a weak base. Now remember, these were all strong acid conjugate, these all have strong conjugate acids, so we call them weak bases. They all have an anion, so they all have a negative charge, and they either have are very polarizable or have some kind of resonance contributor. So those are weak bases, but good nucleophiles. Okay. Now, in the weak bases, these are all sort of kind of, this is the strongest acids or the carboxylic acids. This is a weaker, the chloride here, okay. These are weaker bases. These are all weak bases, but they are a fair nucleophiles. Remember, chlorine's a fair nucleophile because it's not very polarizable. Okay, and that gives rise to our strong unhindered bases. Okay, so these were weak base, weak base. Our strong unhindered bases, notice they're oxygens with a negative charge, are good nucleophiles. And they're good nucleophiles because they're small, they can get in there and do Sn1 reactions, but they can still act like bases, okay? The next thing we have is bulky bases. So sterics tell us that these things cannot act as nucleophiles because there's just too much stuff around this to act as a nucleophile. So they're poor nucleophiles, but very strong bases. Okay. And we're going to use these a lot in our next chapter. So make sure you identify those. And then we have weak bases, poor nucleophiles. Okay. What do we mean by weak bases? Well, okay, look at our acidity chart there and what they are. But they're poor nucleophiles because most of them don't have charge, or the charge is spread out over so many different atoms that it is not very useful. So these tend to be the water and alcohols. So these are weak bases, but poor nucleophiles. And so these tend to undergo Sn1 reactions. These tend to go on Sn1 reactions. These can go Sn2 reactions because of the better nucleophiles. Okay. So Sn1 reaction is a bimolecular reaction with one hump on the activation. On the diagram, polar aprotic solvents have a higher activation energy and are therefore slower. Polar protic solvents have a lower activation energy and are faster. Okay. In our Sn1 reaction, we have a transition state. We always form a carbocation. And the polar Protic solutions, the more polar the thing is, the faster they go, because the easier it is to get through that transition state. The less polar, it can't support the ion as it's leaving. There it gives a much higher transition state to form your intermediate. And SN1 reactions always have 2 humps. SN2 reactions always have 1. All right, questions on that? Okay, I think that is that. All right, here, I'm going to stop sharing for a second. And if you have any questions, I'll entertain them now. I'm looking for my next set of slides. So, past research. Oops. All right, hang on. No, that's not. I've lost my slides here. I didn't lose my slides. I just can't find the one that I was going to present next. Okay. I'm trying to download the slides right now. Oh, I know where I can go. Here we go. All right, I'm just going to email these to myself and then I will start again. Okay. All right, so in our chapter 6, we learned a lot about mechanisms and our SN1 and SN2 type reaction. Closely related to this is our E1 and E2 reactions. So those are elimination reactions, but they use the same premise of nucleophilicity and basicity. Let me see if it shows up. Yeah, there we go. All right. So let me go ahead and share my screen again. Share screen. All right. Let me see my slide. There they are. All right, good. Okay, I'm gonna look at my participants list. There we go. Okay. So can everybody see my slides for module 7.1? Okay. All right, so what we're going to do here is we're going to look at that same kind of stuff we were looking at on the last page of chapter 6.3 and look at a different type of reaction, okay? And this type of reaction is, instead of nucleophilically substituting something off the ring, what we're going to do is we're going to remove that alkyl halide and a hydrogen to form a double bond, okay? So this is the follow on to the SN1, SN2, and we have an E1 and E2. Okay, so in the case of an elimination reaction, we're going to use a base, and it's going to remove a halogen and a hydrogen from two adjacent carbons, giving us a double bond between them. Okay, so we need to figure out which hydrogen is going to be removed and where your double bond is going to form. Okay, so imagine we have a leaving group that we have here, usually a halogen, but instead of doing that substitution reaction, we do something else and it forms that double bond. So we've eliminated a hydrogen and the leaving group and created our change from our sp3 hybridized carbon to an sp2 hybridized carbon. Okay, so the first thing we have to figure out is that where the different types of things are. And so when we label these carbons that we're looking at, the group that is the reactive group, the carbon that has the reactive leaving group species on, is what we call the alpha carbon, okay? And that is called the alpha carbon because that's where the leaving group is going to leave, and so that's the first thing that has to leave. The next thing we do is we go out from that and look at the next carbon over. That's our beta carbon, okay? And then of course, if we go one more over, that's our gamma carbon. Okay? So it's very important because when we do these eliminations, we're going to remove our leaving group from our alpha carbon, and we're going to remove a hydrogen from our beta carbon. Okay, so that's why we're labeling these systems. Notice that in this case, our functional group is our ketone here, and so our alpha and beta carbons go off this way. Our alpha carbon in this case has two alpha hydrogens on it. Okay? So those are the hydrogens that are on that alpha carbon. There's not going to be an alpha hydrogen bonded directly to our leaving group. So, and then of course, our beta carbon has the hydrogens and our gamma carbon also does too. Okay. This nomenclature will help us figure out exactly which hydrogen we're going to remove during the elimination reactions. Okay. So when we're thinking about, I can remove a hydrogen from this side of it, or I can remove a hydrogen from this side of it, which one does it do? Well, when we're thinking about which hydrogen to remove, which set of alpha hydrogens to remove, we have to think about the stability of the product formed. Okay? So in the case of alkenes, the more substituted the alkene is, the more stable it is. And so if it's more substituted, it's more stable. And if it's more stable, that's the product it will form during our elimination reactions as our primary product. Okay. So in this case here, we're looking at a relative rate here. We have a terminal or an alkene with only one R group on it. So this is one R group right here, and it is the least stable up here. We have a huge reactive energy here, exotherm during their making it have the least stable, storing the most potential energy, followed by our cis configuration. Notice these are both on the same side of the double bond. So that's our cis configuration. Our trans is a little more stable because they're spread out a little far apart. And then we have our two substitutions on the same side. Excuse me. Those two substitutions on the same side are more stable than the cis configuration because we have this, this repulsion from here, so that's a little more stable. This is more stable. I don't remember why, it's just more stable. But here, these are all di-substituted, two different R groups on that alkene. This has 3 R groups on that alkene, this has 4 groups on that alkene. So when we're thinking of our product, which product's gonna form, we wanna think about this stability scale in the fact that, oh, if I take alpha hydrogens from this side, I get a cis product. If I take alpha hydrogens from this side, I'll get a 3 substitution alkene, a 3rd substitution on my alkene, and it will form that more stable alkene whenever possible. Okay. Hyperconjugation. And it's partially due to hyperconjugation, and then the second part of it is due to sterics. In the case of our multiply substituted double bond, remember our double bond are p orbitals here, and we can hyperconjugate to 2 R groups on this side, 3, 4 R groups on this side, giving that double bond a high level of stability. Here we can hyperconjugate 3 times. Here we're hyperconjugating and stabilizing one whole side of that reaction of that there. We have about the same hyperconjugation here and here. The only reason this one is a little less stable is because of sterics. And then our mono-substituted only has that one thing that it can draw electron density from. So that's why it's the least stable of the set. Okay. So when we think about our elimination reactions, E1 reaction, it's analogous to our Sn1 reaction in the fact that we form a carbocation. Okay, so it's unimolecular. We form one carbocation there, and then the proton is removed from an alpha carbon. Okay, so that's how we do the reaction, which means it's like an Sn1 reaction, but we end up forming a double bond. Okay, so let's look at the steps here. Now, in this case here, we're using a polar Protic solvent to go ahead and break our bond, giving us our carbocation here. Okay. At that point, we have more solvent in here. Ethanol is acting as, in this case, a weak base. Okay. And it has 2 choices. It can either act as a weak base and pull off a hydrogen, or it can act as a nucleophile and form the substitution. Okay. And in this case of methanol here, if it forms that substitution product, it gives us our protonated alcohol, which actually then can be deprotonated by more methanol to give us our ether. And in this case, we get 80% of it is that species. However, if it acts as a base and pulls a hydrogen off the beta carbon, so this was our alpha carbon, and pulls off a hydrogen off of beta carbon, we'll end up with our neutral product, which is this propene, and our protonated methanol right here. So in this case, we have a competition between Sn1 and Sn2 because we have a weak base that is still a moderate nucleophile. It's a poor nucleophile, but it can act either way when it has that carbocation. So in most cases, there's a competition between an Sn1 and Sn2 if you're using a neutral solvent as a nucleophile, or in this case, the base. Okay. Okay, but do you see that first step is the same in the Sn1 reaction, the fact that we form that carbocation. The second step is removing a beta hydrogen. Okay, so let's dig into that a little deeply. Oh, right at 150. So this is the last thing. 1232. Yeah. Okay. So let's look at this last one in a little more detail here. Again, because we have a polar Protic solvent, we can hydrogen bond to our bromine, making it easier to leave to give us our carbocation. And then once we form our carbocation, in the case of using it as a base, we're going to use the lone pair from here to reach out and start grabbing that, kicking the electrons in. When it kicks the electrons in, it then hybridizes so that one electron is in a P on the alpha carbon, one electron is at the P on the beta carbon, and we now have a double bond between that alpha and beta carbon, giving us our product here. So the electrons from the hydrogen here are the ones giving us our pi bond in our product. Okay. All right, and so let's just look at the reaction mechanism, energy diagram, and then we'll quit for the day here. So if we look at the energy diagram for this, we see that the first hump is that formation of the carbocation to give us our intermediate. And so that's the same for both of them, whether it's an E1 or an Sn1 reaction. Now, depending on the height of the activation energy right here to get to that next step, that's going to determine what your major product is. In this case here, our methanol is acting as a weak base, making it harder for it to get to the transition state to give us our elimination product as our major product. Remember, it's only 20% here. The reason it's only 20% is that activation energy barrier is higher than the SN1 activation barrier. Because that SN1 activation barrier is lower, we end up with 80% of it being that SN1 product. Okay. So if there's a competition between SN1 and SN2, SN1 and E1, how can we sway it to our preferred elimination product? And I want you to think about that until we meet again on Wednesday. Okay, I'm gonna go ahead and stop recording. You can hang out and ask questions.